We've now arrived at the topic of energy, which corresponds to chapter 4 in the textbook. I've drawn it kind of large here because the concept of energy is very important and one of the most fundamental things in this course. In fact, almost everything that we do from now on can and will be formulated in terms of energy rather than forces. This is advantageous not only because energy is more fundamental, but also because energy is a scalar and force is a vector, and it's easier to work with scalars than with vectors. So the first form of energy we're going to work with is something you're very familiar with, and that's the kinetic energy. So if we take our prototypical particle here, and we're going to give it some velocity, like that, some velocity v in some direction, and the particle also has a mass m. You all know that the kinetic energy, which we're going to designate with a T, that will be our standard letter for kinetic energy. That's going to be 1/2 times the mass of the particle times its velocity squared. Now we can rewrite that a little bit if we like. If we're working with the velocity, we know that's a vector, so this is really the same thing as writing 1/2 m vector v scalar vector v. So that's the kinetic energy. Now let's look at what might make this kinetic energy change over time, and we'll do that just by taking its time derivative. Okay, so that, and if we apply that to this one, what we will get will be the following. These two terms are obviously the same because the scalar product commutes. Like that. I'm going to put this together, and we can see that what we have here is just the time derivative of the momentum, right? mv, time derivative, mass is constant over time, so that just becomes equal to vector p dot scalar v. Now we know from Newton's second law that the time derivative of the momentum is the net force that acts on the object. Right? So we have, presumably, some forces that act on this object too. So according to Newton's second law, then, those forces can cause a change in the kinetic energy, which is just F scalar V. So we can see that if things are the way I drew it here, with the force being perpendicular to the velocity, then actually the kinetic energy doesn't change. That makes sense, right? Because the force is then pulling perpendicular to the velocity and doesn't change its magnitude, and therefore the total kinetic energy, which only depends on the magnitude of the velocity, stays constant. So basically what we obtain is that T dot equals the force scalar the position time derivative of the position vector r dot. And this is the same, of course, as dt equals F scalar dr dt. I can then take this and multiply by dt, and I will then obtain that the change in kinetic energy equals the force scalar some differential displacement. So if I move a short distance, dr, my kinetic energy changes by the amount force scalar dr. This is something you should be familiar with from 2305. However, in 2305, the forces were constant and displacements were along straight lines. That is no longer necessarily going to be the case. We're going to treat now the case of general motion. So we have a particle and starts at point A, and then it moves in a trajectory to point B. And in order to figure out now, let's see that we want to figure out the change in kinetic energy of this particle from point A to point B. What we have to do is take this motion and divide it into small pieces. differential displacements. So this would be, for instance, dr1, dr2, dr3, etc. It's a little hard to see my subscripts here, but that's what I'm writing. So if I then want to figure out now, let's say, the kinetic energy change from B to A, that's TB minus TA. It's going to be the sum of the kinetic energy changes during each of these little line segments here. So that is, of course, then the sum of F scalar dr alpha. And as we're making these line segments shorter and shorter, this then becomes an integral. Becomes the line integral from A to B of F of R scalar dr. So if you're not familiar with a line integral, I suggest you look at the math interlude on line integrals. You will be asked to calculate a few of these, both in homework and probably on the exam. But as I'm going to now assume that you know how to work with these. But in any case, the result that we get is that the change in kinetic energy is the integral F dr. All right. So this integral here is known as the work integral. It corresponds to the total amount of work that's being done on the particle. Right? And this relationship here is the work-energy theorem. So we can also write the work-energy theorem as delta T going from A to B equals the work done on the particle from A to B. Simple enough. Now, one thing that needs to be pointed out is that this work integral here results in general from the work of several forces. So this is due to multiple forces. So when we take the integral of F scalar dr from A to B, what we're really working with here is the net force. So we could write this as just replaced F net here with the sum of all the forces acting on the particle. And then we can take the sum outside of the integration sign. So what we get then is that the total work done on the particle is really the sum of the work done by all the individual forces acting on the particle. And this is actually a convenient way to calculate the work. You are perfectly able to split off the work of different forces separately and add them together after you've calculated each individual work. So that we obtain then that delta T is just the sum, so the T from A to B is the sum of the work of each individual force going from point A to point B. Now, the work-energy theorem is valid for any kind of force. What we're going to do next, though, is look at a specific kind of force where the work done is not dependent on the path between 2 points, but only on the starting point and the ending point. And those forces are known as conservative forces. And that will be the subject of the next video.